Okay, so now we're giving you a short demo here on the use of Multisim. I've opened here a new file, and what I want to show you is that Multisim is a Windows-driven software. I do think that they have an option for other platforms, but Windows is the most used platform. So notice that it's got a menu just like any Windows software with helps and all that. Help actually is a very good way to be able to do good things with it. And so let's take a look here at this software and how is this software used for purposes of designing various kinds of electronic systems, if you will. So I'm giving you a short introduction to the software just before we do a little bit of experimentation with this software. So you can place components. That's one way to call out the library of components. And as that happens, you could also, call out the text box. I'm writing here, this is a demo of Multisim or a demo with Multisim. Basically, you just go to place and then text is the option that I selected. There's also a shortcut just like any other software that you can actually use for this. But for example, that's one thing you could do. Place text. Sometimes you will have to document your designs with labels and such things. Now I'm pulling up a source from components, and I'm pulling up a ground, and again you can find any part by either using the place component. I think my screen is not being captured completely. There's something that this software is missing as I pull them out, but it should be from the place uh, library or submenu that I'm pulling this out. And as I'm doing this, I'm bringing parts to be able to start a basic circuit demonstration here. To join or connect the parts, you basically just click on one end and then drag and click on the other end. And that's how this is all completed. So we got a circuit here that has a source, a ground, a switch, and a little load, a lamp. And now I can switch on and off by just uh, hitting the A character 8 on the keyboard. That's how you do that. You can also place anything else. I'm going to change the value here. 15 volts is a little bit too much for the lamp. So now I have replaced that for a 5 volt lamp, 5 volt source lamp. And that gives me a better idea of, testing this lamp. And of course, I was running that. You notice that I stopped the simulation. And that's really what you could do with Multisim. A lot of this experimentation, there's a lot of good video tutorials out there that you actually can use for knowing how to use. But the assumption here, you have a little bit of knowledge, maybe you don't, about electronics, electricity, and whatever circuits that you're working on before you build, or maybe some of you are going to be learning as you go about this kind of application. So here it is again, the circuit. I'm testing that out by just hitting the A key on the keyboard. Okay, so that was that. Okay, let's take a look here at the building of an actual digital logic circuit. We're going to be presenting in this short session, less than 30 minutes, three of the most fundamental logic gates. and those gates are going to be the um, NAT or and AND gates. And so I am going to be, pulling the components from the library, and there's multiple ways you can do that. You could go to place, and then component. You could search for the component. You could also go to the sub menus of the library and find all the components. For this particular circuit, we need a power source. That's a B sub CC. We also are going to need some resistors um, that you can bring on from the main toolbar. You also can use a copy and paste function, just like any other Windows-based software. Control C, Control B, and that way you can replicate the components. So once again, I'm needing some resistors in here, and I may just do that. You can also change the value of these resistors as you go forward. The value can be changed, and you're going to see that. So I am in that process exactly, uh, getting all the parts and components that I need to demonstrate to you the function of these very basic logic gates, which are the NAT, the OR, and the AND. You're gonna see how we build them, right? And of course, because this is the first actual demo, I'm gonna build the whole thing. But if you have a template like a file that you started, you can actually use that file and just modify what you need on that file, and eventually just rename the file. We're gonna see how that's done here in a little bit. So anyways, I have another element here, which is a double throw single pole switch. I'm gonna turn around this switch. You can actually rotate these components, also relocate them wherever you want. Just hold down, drag, and release, and you can place them whatever you want. And as you do that, you will get the parts where you need them. So I'm bringing the indicators because I want to have a couple of pilot lights for this particular NOT gate. One that will be at the input, and the other one that will be at the output of the gate we're going to be analyzing, which is the NOT gate. The NOT gate basically is a type of gate that will take in a signal and reverse that signal out through the gate. So if the signal is high at the input, the output will be low, and vice versa. If the signal is low, the output will be high. That's the reason it's called an inverter or a NAT gate, because it does invert the data or the signal that you put in its transform, and it's an important basic logic gate, the NAT gate or negated gate. Okay, so here I go with more components that I need to place. Here is the 7404 gate, which is the NAT gate that we're going to be using for this particular short demonstration. And once I get all the parts, then I'll start kind of relocating them, and not only relocating them but also connecting all the pieces together. All right, so I'm going to also bring some multimeters, basically voltmeters, to be able to know when a voltage is present or not present. Voltage presence indicates a true or high statement in digital logic. Voltage not present indicates a low, ground, or false statement, if you will. And so that's the reason why I'm pulling out these meters here, voltmeters, that we're going to place here as we go forward with our circuit creation. Bear with me. You can replicate what I'm doing or simply design something different, but the idea is to give you a notion of how this digital logic gates work, and particularly the NOT gate, the very basic NOT gate. Notice that I'm actually rotating around some of the parts. I need this part to have two different inputs, high and low. that travels through the same port or channel. So I rotated that part, and I'm now moving it down. To rotate a part, just click on it and right click, and then you're going to have rotate by 90 degrees or more. And that's how parts are rotated. Okay, so I'm replacing the components and zooming in a little more so you can see all the parts that I have here, while I get my parts ready for the demonstration of the NOT gate, the very basic and fundamental logic gate that computers and technology, which is digital, works on. All right, so here we are trying to get all those parts in place to design, test, and simulate our circuit. And this could be something that it's part of an actual circuit, an actual application. But before we talk about that, you need to understand the foundations of how it is that these gates work and what it is that they do. So hopefully this little demo is going to help you accomplish just that. All right, I need another resistor in here, and I may have to change that resistor value. I'm gonna change and rotate that resistor so that I can manage to put it where I need to put it. And once I have them all aligned, I'm now going to connect. Notice the connecting is as easy as clicking on the end of the component and drawing and dragging the pointer to the other end, right? That's how that's connected. Click and drag, and as you do that, then you connect to the other end. All right, so that's what I'm doing, a connection between components. And I'm going to place this meter in here. I might have to change this meter later on, but let's just throw it in there for now as we're building this circuit. Move the resistor down, get all the other parts connected, relocate. I'm sure there is a function to uniformly distribute parts on the canvas here in Multisim. I just don't remember what that function is, and we'll have to find that out later on. But for now, we're just manually moving each piece and connecting them all together to be able to do some tests here at some point, right? As we get to the end of this. All right, so this is the NOT gate, probably the one that's going to take us the longest, just because we're creating this from scratch. That's not going to be the case for the upcoming design. We can use a template and just modify that template and go from there, right? So you're going to learn that trick. So you don't have to replicate every little piece, but use a template, modify it, rename it, and then you have a new file. So here I'm connecting everything. Once again, just like so. Click and drag, click and drag. Make sure you have those dots connected right. Our circuit is ready to be tested. Okay, I'm gonna have to run the simulation. So I'm just testing, and then with the space key, you're able to open and close that circuit. Okay, so now I have the simulation running. I have a little bit of an issue here, and the issue is that this particular gate, as I switch it over to high, the output should go low, and as I switch it over to low, the output should go high. But it's not doing that, so I might have a little bit of a trouble here. I'm gonna have to troubleshoot it and do a few little modifications for that purpose. Okay, so we're gonna do it together, and it's a good learning lesson for you as you learn a new software to know what could be run. Sometimes it's just a wire that is open or an extra wire that you have on the circuit. But let's stop it here and try to see where the problem could be here to troubleshoot it and fix it, and hopefully we'll find a solution for that. All right, so we're trying to fix so that the NAT gate behaves how it's supposed to behave, and that is when it takes a high signal, the output should go low, and when it takes a low signal in the input, the output should go high. That's what it should be doing, but it's not. I wonder if I need to change the value of the resistors because they're a little bit different. So I'm going to change one of these resistors to make it equal to the first one. I'm flipping the switch with the space bar um, and not accomplishing what I need to accomplish. And so that means I might have to. All right, so let's check out here what's happening. It looks like what I had was the wrong excuse me. I had the wrong component or the wrong connection. I actually had an ammeter here in the middle, lower meter, and that was not what I meant to have. I was supposed to have both voltmeters on both branches, right? To monitor that voltage. So I am gonna go ahead and change that. And as that change takes place, I now should be able to properly um, check the function of this NAT gate. So I am going over that. Notice that I made a change. Again, the voltmeter in the center, I changed that because I had an ammeter mistakenly. And now the circuit should be able to do what it's doing. You see that? So I can flip the switch, you see, and the output is responded. When the input's high, indicated by the light being on, the output goes low, and vice versa. When the input is low, the output goes high. And so this is the NAT gate function, right? And it's doing what's supposed to be doing. So I'm glad that I was able to troubleshoot it. Okay, so I'm gonna introduce another function here in just a little bit as we go forward. Okay, do a little troubleshooting in here. Okay. Okay, so what I'm gonna show you here is a shortcut. Instead of us building every file for every circuit, I'm gonna just use the template I have here and use all the parts that I have on the canvas and add on and eliminate what I don't need. That should speed up the process to build the next logic gate, which is the OR gate, right? The OR gate. So we have gone over the NAT gate. Now this part is going to introduce the OR gate, and this is going to be as simple as simply changing the digital logic gate, right? So I can easily modify this, and of course I need two inputs because it's going to be a two input OR gate. So I'm going to need to have another switch uh, so that I have control over two inputs individually, but the same sources and resistors and light indicators are going to be the same we're going to be using for this OR gate. And so that's how you can take advantage of an already made profile or template. So I'm going to just right click on this one here on the NAT gate, and notice how I just changed uh, from the NAT gate to the OR gate. The 7432 is the OR gate, and that's the one that I want. I'm gonna even replicate this switch because I need a second switch. Control copy and paste, and now I have a second switch. So the idea is shorten the time for development as you basically use a previously designed system, and just want, like I said, add on what you need to add on, remove what you need to remove, and subtract what you need to subtract. So I am in that process right here. Adding a new switch, not only adding a new switch, but also having the ability um, to add a new gate, and with that new gate is going to be the possibility of connecting the gate as supposed to do. So this is the OR gate, the truth table for the OR gate, which we're going to present at the end is a truth table that requires any of the inputs to go high for the output to go high, and when all inputs are low, the output should be low. And so let's build this OR gate together here. You can just replicate what I'm doing. Hopefully by this time you have the software to do that. Uh, and now you will know how the basic logic gates, NOT, OR, and AND work. And you can use them in your own projects and designs, electrical circuits, and digital logic gates. So here we go. You're going to notice that building this OR gate is going to be faster than building the NOT gate, which is simpler, but because we needed to bring all the pieces to the canvas, that took us a little longer than normal. So as we have this, I'm just making adjustments here before we test this out. The OR gate is what we're going after, and of course after the OR gate we're gonna build the AND gate, which is the third important logic gate for this circuit. So again, we're just kind of reshaping things out, getting things ready, and this is almost ready to be tested. We got our two inputs, space bar. The trouble with the space bar, how it is, but before we do that, let me just put another meter here, a voltmeter that's gonna indicate voltage at the input of the upper input, and we have also a meter at the lower input of the OR gate. All right, so we got 3 meters. Each of them is monitoring the input at both inputs. So now I'm gonna give it a shot, and of course when I do spacebar, what's happening is switching the two switches because they're controlled by the same bar, the same spacebar. And so I'm gonna need to change here, double click, and I can change that so that I have control over each of the ones. I'm gonna change the label from a space to a character A and B, and as I do that, then I'm now able to control individually the inputs of this OR gate. Again, the OR gate 0 0 or low low gives us a low. Let's run it. One high and the other low gives a high. The other high and the other low give us a high. And when they're both high, we also are going to have a high. So that's the OR gate in operation. We're getting to the point where you now have the knowledge of how the OR gate, digital logic OR gate works, right? And so we're going to start probably a new circuit out of this. So one moment here. And so we have just finished up building the OR gate. One less gate we're gonna build is the AND gate. And to do that, we're gonna do it as simply as just basically replacing the part. Right click, replace part, and as we do the replacement, we can change the OR gate into an AND gate. So right click, replace part, and we're going to have now an AND gate, which is a 7408, label 7408 gate. And really, this is all we need to do to make the AND gate. So notice how we went from a little bit difficult building the first gate, the second a little more, and then the third one easy by just simply replacing that. So we can run the simulation. This particular AND gate requires both inputs to be high for the output to be high. Whenever any combination of 1 and 0, high and low, low and high is present, the output is going to be low. So they both need to be high for the output to be high. And that's how the AND gate operates. And that's the basic operational principle of the AND gate, right? Both inputs need to be high for the output to give us a high, all right? Or else the output is going to be low, All right, so we have built the three basic logic gates: the NOT, the OR, and the AND. And you can save individual files for this. I'm gonna use the text labeling editor to make a little review here before we finish up this demonstration. So this was the three basic logic gates. Again, in review, the NOT, the OR, and the AND gate. Those are part of the foundations of digital logic gates. NOT, OR, AND. Okay, and along with those foundations, we're going to create here the truth tables so that we can review the operation of each of these logic gates. So the three tables, as we said before, needs to reconcile so that the systems can do what they need to do. So I'm going to create more text here just to explain what I'm talking about, and it's going to allow me to create the not truth table, TT for truth table. And this particular gate has a single input and a single output, so you can label that input however you want. So we're going to just label input A. It's going to be A, and the output is going to be not A, right? Because that's exactly what the gate does. The input is A and the output is not A. And as we studied and demonstrated, the conditions are that if A is false, then not A is true, and vice versa. If A is true, then not A is false. And that's how you can represent the logic of the NOT gate configuration or function, right? Let's do the same for the other gates that we had before, right? The other gates was the OR gate. So we're going to create another text table here to indicate the OR gate. I'm just going to copy and paste and modify, take advantage of copy and pasting. And so the OR gate that we demonstrated had two inputs, and we're going to call those inputs A and B. I'm just arranging the table here for you to review these concepts. And we're going to have input A and input B, right? Two inputs both for the OR gate and the AND gate. And of course the output, we can label that output X, Y, Z, whatever we want, just for conventional purposes. So whenever we have one false, the other true, the output is going to be true, right, for the OR gate. And whenever we have A true and B false, the output will still be true. But of course there is a condition, and that's when both inputs A and input B are not true, the output will be not true, right? So this particular OR gate requires that at least one of the inputs be high for the output to be high, right? And that's what we're trying to summarize here as we close up this basic logic gates training with Multisim. All right, so that is the table for the OR gate, right? And of course, when both of them are high, the output, of course, is going to be high. That's how we express a truth table for the OR gate. And of course, we have the last one. I'm going to copy and paste the OR gate truth table, and the last one is going to be the AND gate. And this AND gate, as we know, has also two inputs A and B. But the difference here is that except for when both inputs are high, everything else will provide a low output, right? So that is the AND gate. Both inputs have to be high for the output to be high. And that's the end of our demonstration with the basic logic gates. Thank you so much for your attention. Give me your feedback. Hopefully this is useful information about digital logic gates. We'll be seeing you on another training in the future. Thanks so much. God bless you. Take care of yourself. Bye-bye now.